right, so let's look at your test review. All right, so for your first couple, you were given this graph and you were asked to find some limits, okay? So for this first one up here, we've got the limit as x approaches -3 from the right. So if we come over here to our graph, here's -3. So approaching at from the right-hand side is going to be this red one right here. So you can see that that's approaching a y value of 0. All right, if we're approaching -3 from the left, that's this light blue one over here. So coming at -3 from the left, you can see that's approaching a y value of -2. So since the limit from the right was 0 and the limit from the left was -2, then the overall limit does not exist. You also can see it, like if you look at the picture over here, like you can see there's a gap between those 2 points. Remember that both pieces of the graph have to be converging on that same point in order for you to have a limit. All right, so then the next one, we had the limit approaching 0 from the right. So that's going to be our green one over here. So if we approach 0 from the right, you can see that's going off to positive infinity. So again, what we're saying there is the limit doesn't exist, and the reason it doesn't exist is because it's going to infinity. Then we had the limit approaching 4 from the right. So if we come over here to +4, so from the right-hand side, that looks to be approaching 2, and from the left-hand side, that looks to be approaching 2. Those are our 2 navy blue ones there on the graph. So if the limit from the right and the limit from the left both equal 2, that limit is 2. So if we skip down here to just a second to number 8, you can see that limit is going to be 2. Then they try and trick me because they ask me, but wait, what was f of 4? Well, when x is equal to 4, the y value is +1, but that is completely irrelevant. I don't care what's going on at that point. I only care about what's going on as I approach it from the left and from the right. So what's going on at f of 4 is irrelevant. We can find it, obviously, but it doesn't affect our limit. All right, then the next one they asked me was, which of the following would be a vertical asymptote? And so remember that when you take the limit and you get either infinity or a negative infinity for your answer, there's going to be a vertical asymptote there. So when we took the limit approaching 0 from the right, or you can see it from the left as well, that went to infinity, then that means that there's going to be a vertical asymptote there. All right, then they asked me what kind of discontinuity is there at -3. So if we come back over here to -3, remember that's where you had like the jump in your graph. Like if I'm drawing this with my pencil, I'm drawing down here and then I have to pick up my pencil and jump up here to continue my graph, right? So that one has a jump discontinuity. All right, then they asked me what's going on at 0. We've already said that it's going to infinity at 0, so that's an infinite discontinuity. And then the discontinuity at 4, so if we come over here and we look at 4, if we just redefine that one value right there at 4, that one point, it would be continuous. So that's our definition of removable. All right, so then the next one we had for number 13, I asked you to evaluate it by hand, but I told you that you also would need to be able to make a table of values for that, or look at a graph and make sure that all 3 gave you the same thing. So this is what I'm talking about. All right. So first off, doing this by hand, this is a rational function. So rational functions are going to be continuous within their domain. So basically, as long as I don't get 0 in the denominator, I'm fine, right? So I'm going to go through and I'm going to plug in 2, but sure enough, if I do that, I get 0 in the denominator. So not well behaved. So I'm going to use anything in my algebraic bag of tricks I have ever learned to try to make this well behaved. And so I'm going to go through and I'm going to factor my numerator and cancel in my numerator and denominator. So then what I'm left with is just the limit of a polynomial. That's well behaved. I can just do direct substitution and get my limit. And again, watch that limit notation, that we keep writing that limit notation until we actually plug the 2 in for x. And then once we do that, we don't write the limit notation anymore. All right, so then if we were looking at a table, all right, so if I'm finding the limit approaching 2, from the right-hand side, I'd be using like 2.1, 2.01, 2.001. From the left-hand side, 1.9, 1.99, 1.999. And so we just plug each of those into our calculator, and you can see the values that we generate there. Again, remember the number of decimal places isn't important. We're looking for a pattern. So I just need to be able to see that it was 3.9, 3.99, 3.999. The next one would be 3.9999, so that we can see we're getting closer and closer to 4 from the left-hand side. From the right-hand side, 4.1, 4.01, 4.001, we would anticipate the next one to be 4.0001. Again, from the right-hand side, that limit appears to be approaching 4. So what we got on our table backs up what we got algebraically, all right? Then if we looked at the graph of this, so if I put x squared minus 4 over x minus 2 in my graphing calculator and I graphed it, then this is the graph that I would get. I need to be really careful to make sure that I leave that hole in the graph at x is equal to 2, because remember it was undefined there. So that won't be super obvious on a graphing calculator. I mean, if you go straight to that point, it will not have a y value, but there's not going to be like a big gap in the graph at that spot unless you're zoomed in. So that's where our knowledge comes into play, that we know this doesn't exist at 2, that there's a hole in the graph at 2. But if we're approaching this from the right-hand side, you can see that does look to be converging on a y value of 4. And from the left-hand side, same thing. So both pieces of the graph converging on the same y value, and it's a y value of 4. So what we found algebraically, numerically with a table, and graphically, all giving us the same thing. Okay, so then for our next set of problems, for 14 through 18, these were not making a table of values. We're not looking at a graph or anything like that. We should be able to do these by hand. All right, so for this first one, again, this is a rational. So the first thing that I would do is try to plug straight in. I get 0 in the denominator, so that's not going to work. That does not mean the limit doesn't exist. That just means it's not well behaved. All right, so I'm going to try and do anything in my algebraic bag of tricks to simplify it. So if you'll notice, I'm going to FOIL x plus 3. So I'm going to do x plus 3 times x plus 3. So that's where we're getting this x squared plus 6x plus 9. Our 9s would drop each other out. And then we're just left with x squared plus 6x in our numerator. We could take out a greatest common factor of x. So we would just be left with x plus 6, because the x in the numerator and the denominator will cancel. And so then I have the limit of a polynomial, which is well behaved. I can plug in and do direct substitution. All right, then for 15, if you'll notice, this is the overall limit. It's not from the left or from the right. It's the overall limit. So when I plug in and I get the square root of 0, flashing lights need to go off, because that will not exist when it's the overall limit. It will only exist from one side or the other, either from the left or from the right. If they had asked me for it one-sided, I might have come up with an answer. I got a 50-50 shot, right? But when it's the overall limit, it will be does not exist every time. All right, so then our next guy is that type of problem that we do with logic, where if we take the limit of a constant, we get that constant. So that's staying the same. But down here in the denominator, if we're approaching 4 from the right, so like we're using 4.1, 4.01, 4.001. When I subtract 4 from those, I'm going to get 0.1, 0.01, 0.001. That denominator is getting smaller and smaller and smaller. Now, every one of those values was positive, but we were getting 0.1, 0.01, 0.001, getting smaller and smaller and smaller. So If our numerator is staying the same and our denominator is getting smaller and smaller and smaller, then our overall fraction is going to get larger and larger and larger. So this is either going to go to infinity or negative infinity, and I just need to check my signs to see which one it is. So if we come back over here, this was negative, but this was positive. So a negative divided by a positive is going to give us a negative infinity. All right, so then for the next one, again, if I try and do direct substitution, I would get the square root of 9, which is 3. So 3 minus 3 would be 0 in the denominator, so not well behaved. Remember that when you have a radical either in your numerator or your denominator, you can rationalize that. And we rationalize by the conjugate. We multiply by the exact same numbers that we had here in variables, but just the opposite sign in between. So here I had a negative, here I'm going to use a positive. And whatever I do to the bottom, of course, I have to do the same thing to the top. All right, so if we multiply that out, I'm going to leave the numerator alone, so I'm just going to bring it all over, not going to distribute or anything because I'm hoping to cancel in just a second. But down here in our denominator, we're going to have square root of t times square root of t, so that would be t. And then square root of t times 3 would be 3 square roots of t. Negative 3 times square root of t would be negative 3 square roots of t. And then negative 3 times positive 3 would be negative 9. So our inner and outer will cancel each other out, and that leaves us with just t minus 9 in our denominator. Then that cancels with the t minus 9 in the numerator, and then what I'm left with is just the limit of a root and a constant, and those are well behaved as long as I don't get 0 under the radical. So if I plug in, I get the square root of 9, which is 3, and then 3 plus 3 would give me 6. All right, then for number 18, so here's another one that if we do direct substitution, we get 0 in the denominator. Not well behaved, doesn't mean it doesn't exist. So this time I had a radical in the numerator, and I can rationalize the numerator just like I do the denominator. So I'm going to go through and I'm going to multiply by the conjugate again. So notice it's the exact same thing, just the opposite sign in between. And whatever I do to the numerator, I have to do the same thing to the denominator. So in my denominator this time, I'm just bringing that whole thing along. I'm not going to change it because I'm hoping to cancel. All right, so we're going to keep this denominator exactly the same down here. So we're just bringing it over in hopes that we'll be able to cancel it in just a second. And then in my numerator, I'm going to do square root of t squared plus 16 times square root of t squared plus 16. And that's going to give me the square root of t squared plus 16 squared, right? The square root and the square drop each other out and just give me t squared plus 16. All right, then I'm going to do the square root times 4, and that would be a positive 4 square root. And then I'm going to do a negative 4 times the square root. So there's our negative 4 square root. And then negative 4 times positive 4 is going to give us negative 16. All right, so if we see what we've got left, remember we said that the square root and the square dropped each other out and just gave us t squared plus 16. These two canceled each other out, so I just have this minus 16 to bring down. So my 16 and negative 16 cancel each other out, and that leaves me with just t squared in my numerator. We had not distributed our t squared down here in hopes that it would cancel, so sure enough, you can see the t squareds drop out here. And so then I'm just left with 1 over the radical, all right? So remember that I can just plug into my radical as long as I don't get 0 under the radical, I'm okay. And so if I plug in, you can see I get the square root of 16, which is 4. And then we still had that 4 sitting there. So 4 plus 4 gave us our 8 in our denominator. So 1/8 for that guy. All right, so then for the next set of problems, we were working from our piecewise defined function. All right, so they ask us to find the limit as x approaches 3 from the right. So from the right-hand side, that's going to be this top piece up here. And so I'm going to plug 3 in. That's a polynomial. It's well behaved. I can just do direct substitution, so I get 0 for that one. Then they want the limit approaching 3 overall. So if I need the overall limit of 3, I need the limit from the left and from the right. So I need to go find that from the left, even though they didn't ask me for that. I got to go find that to know the overall limit. So if I take the limit approaching 3 from the left, then those would be values that are less than 3. And so that's going to be this piece right here. And when I plug in, I get 0. So since the limit from the right equaled the limit from the left, the overall limit would be 0 at 3.